네, 안녕하십니까. 요번 시간에는 우리 이제 지금 지난 시간까지 배운 내용 다음에 여러 가지가 나오는데 나머지는 여러분 이제 노트에 있는 거를 그대로 참조하시면 되고 가장 중요한 정리 중에 하나가 오픈 매핑 디어럼입니다. 오픈 매핑 디어럼이 또 함수 해석학에서의 또 하나의 꽃이라고 생각해도 되는 그런 중요한 정리 중에 하나입니다. 지난번에는 우리가 뭘 배웠죠? 유니폼 바운드니스 디어럼을 증명을 했죠. 유니폼 바운드니스 디어럼이 바로 뭡니까? 예. 유니폼 바운드니스 디어럼이랑 그 다음에 베어스 카테고리 디어럼이 두 개가 있죠. 유니폼 바운디드니스 디어럼은 이제 포인트 와이즈 바운디드면은 유니폼 바운디드 된다는 거고요. 그 다음에 이제 베어스 카테고리 디어럼은 이제 여러분 컴플리트 매트릭 스페이스면은 세컨 카테고리 스페이스가 된다라는 거고. 자, 세컨 카테고리라는 이야기는 이제 그 매트릭스 컴플리트 매트릭스 스페이스가 클로즈드 셋들의 카운터블 유니온으로 표현이 되면 그 중에 최소한 하나의 집합은 인테리어가 공집합이 안 된다라는 거죠. 퍼스트 카테고리가 이제 모든 인테리어가 모두 공집합이 되는 그러한 집합들을 카운터 유니온으로 표현이 가능하다라는 겁니다. 그래서 이번 시간에 우리가 배울 것이 뭘 할 거냐면은 x랑 y가 바나 스페이스이고 그 다음에 a라는 게 x에서 y로 가는 리니어 서젝티브이면서 이제 연속입니다. 리니어 맵이 바운디드라는 이야기는 컨티뉴스 맵이라는 소리죠. 그렇게 되면 a는 오픈 맵이 된다라는 겁니다. 오픈 맵이라는 것은 위상항에서 배운 것 같이 G is open, then A of G is open. Okay, so let's try to prove this one. In order to prove this, the first step is to prove for every R equal positive, then interior of ABR closure is always contains zero element. So 0. So B of R is the ball of radius R centered at 0. Okay. So this is our first step to prove. Well, let's see. First we note that so we A B Y for every K B R K and the closure for each one this guy is belongs to Y, right? Y for fixed R Y and hold countable union is also subset of R. But the first step is we're going to prove Y is the same as the union, countable union of A of, this is the ball of radius RK over 2 and closure, the image of this one. So this is the first step we are going to prove. So so this is always true. We like to prove this part. So I take one element y, small y is in y, then A is surjective. So the map is surjective and there exists Ax such that Ax equals to y. And x is given now. So then we can have the norm of x is finite. So then you multiply by 2 and divide by r. So you can choose integer greater than this number. So we choose k is integer satisfying this one. Then you solve this one for x norms. X norm is less than rk over 2. So which means x is element in B rk over 2. Okay. And the image ax, y equals ax. So here y equals ax. And then x is element in here and y is belongs to this set. And this is obviously subset of closure. Okay, so for every y is in y, y is in y belongs to this one. So that implies y is a subset of this countable union. Okay, So this implies Y is written in so closed subset. Okay. The first step we showed the this is Y is complete metric space. Banach space complete metric space. Metric space is countable union of closed set. These are closed set. Closed set. So using Bayes' category theorem, then at least one of them is non-empty. So there exists the K such that interior of this guy is non-empty set. This is a result of Bayes' category theorem. And then this is the linear map, and this K is actually came outside. These are the same. And then this cannot be empty set. If this is empty set, whole thing is empty set. So let's say V equals interior of A of B R over 2 and closure. So this is a non-empty set. So V is now open and non-empty set. So we choose one element, y0 from V. Then V is open. We know this V is open. So they exist R, S, such that the ball of radius S centered at y0 subset belongs to V. V is also subset of this one. Okay. Now here this one. Now what? So here the graph is y0 radius S. So this one belongs to radius of R over 2 0 R over 2 this one. So the whole thing is radius R over 2, and this is the B A B R over 2, and then I consider this guy. So this is a centered y0, and I move y0 to 0, then this is just B. So now you consider 0 S. Okay, ball of radius S centered at 0. So I consider this guy. This is actually a subset of this one. So you got the ball of radius R. Okay, the image of ball of radius R closure. So we want to show this one, and then here, in order to prove this one, let's take one element here. This is one element here. Y you take B OS. Then so y0 is actually element in here. This is y0, right? So you got the y0 is in V. V is a subset of this one, and you can choose a sequence in B of R over 2. AXN converges to y0. So by definition of a closure, and then y0 plus y is also belongs to B y0s, because y0 plus y minus y0 norm is just norm of y, and norm of y is less than s, right? So this is just true. Then this is also belongs to this element, this set. So then we can choose Gn is a sequence in B R over 2 such that AZN converges to y0 plus y. Okay, this is true. Then AXN converges to y, AGN converges to y0 plus y, and then I subtract this one from this. So AZN minus XN actually converges to y. Okay. Then XN ZN is element in B R over 2, and I subtract XN from ZN. That is called the WN. WN is actually belongs to B of R. Okay. Then AWN converges to Y. So here AWN converges to Y. W is element in B of R. So that means Y is element in A of B of R closure by definition. So this is by definition. By definition, we can show that. So you take I take any element here that it belongs to Y. So we proved this statement. So this is true. So now B of BOS belongs to ABR. Okay. So conclusion here, so we proved this statement. And this guy is obviously contains 0. So 0 is this one is actually a neighborhood of 0, right? A neighborhood of 0 implies 0 is a point, interior point of this set. Okay. And the second step is to prove this is a radius R over 2, and the image enclosure is a subset of B. You know, the radius you increase by twice. Okay, so we want to show this is true. In order to show, let's take one element Y is in here. So Y is in A, B, R over 2 closure. I take one element here. And then we know the interior of this set always contains 0 for every t. Of course, when you take t equals r over 2 r over 8, 2 cubed. So we take this one, 0 is element here, interior point. And this guy contains 0, right? 0, and this minus just take you change the sign in front of the vector. Then y0 minus this set translate. This is translation. This is open neighborhood of y1, right? Because this one contains 0. And y1 is actually the element here, closure of this one. By definition of it here, so this neighborhood of y1, and this set is non-empty by definition of closure. So because y1 is element here, this is non-empty set. So we can choose one element x1 from here, and the ax1 also element in here because intersection, and the y1 minus interior of 2 cubed r. So this is by definition. Then you can write down ax1 equals y1 minus y2. y2 is element in here, so y2 element here. So there's no difficulty so far. Then I can write down y2, you just switch order, y2 equals y1 minus ax1. Okay, y2 is element here, y2 is element of this set. This is the closure, interior obviously subset of original set. Okay, now y2 now. So interior of this one is always contains 0. We know that for every set R, this is contains 0. And then this guy is again neighborhood of y1. So this guy is also neighborhood, open neighborhood of y2. And the y2 is element in here. So this one is non-empty as before. Then I can choose one element x2 from this set, such that a x2 equals y2 minus y3, where y3 is this set. This is exactly the same as previous steps. So you keep this process to obtain yn plus 1 equals yn minus axn. So xn belongs to B of R over 2 to the 2n minus 1. And the yn is element in interior of this set. You see? And the yn plus 1 is the bigger than this one. Okay. So you take in the y3 and then y3 and the y4, you can obtain yns. At the end, we have y1 equals ax1 plus y2, and the y2 equals ax2 plus y3. You see here, yn equals axn plus yn plus 1. And they keep on going. We obtain the y1 equals to summation k from 1 to n a sub xk plus yn plus 1. And then I subtract y1 minus, subtract this one from y1, and then I look at the norm, that's exactly yn plus 1. But yn plus 1 is element in here, this element in here. So yn plus 1 element here. So that means this one is the norm of A is less than R over 2 to 2n plus 1. You can. So do you know why this one true? So interior of this one, you have some element here, and then norm x, b, a, x. Okay, norm is less than y. So you have to look at this one. So finally, when you take n goes to infinity, so this one converges to y1, right? The limit of this one converges to y1. And then here, this is a finite sum. It's A is linear. A is linear. You can write down this way. And also, we want to prove this guy is actually converge. So let's look at this one. The norm of xn is a triangular inequality. We have this one. Each x1 is r over 2. x2 norm of r over 2 cubed, and so on. We have this. And this is less than infinite series. So the sum is 2 over 3. Okay. You take a limit of this guy is less than r. So limit exists. Also, the limit belongs to bxr's norm. So finally, we take x equals limit of this. Oops, 여기 잘못됐네요. 여기가 무한대가 아니라 n입니다. n을 무한대로 보내고, 네. So you take, yeah. You change n. Then y1 equals ax, and x norm is less than r. So which implies y1 belongs to a br. So we finally prove this statement. Okay. So you got the radius of half, and the image closure is subset of a of radius r, both of radius r. So this is very important. Okay, this is step 2. And then finally, we need to prove the map is open. So we need to prove this map is open. How do I prove this one? So our final step is to prove A of G is open whenever G is open. So remember, from step 1 and step 2, we have from step 1, step 2, for every positive t, interior of a bt closure is contains always 0. And then we have this statement. This is very important. Yeah, this is important. So now let's take G is open set. Then for every x in G, G is open. Since G is open, for every x, there exists R positive, the ball of radius Rx subset of G, then we know that 0 is belongs to A interior of A, B, Rx here. So this is why this is true. So here, okay, from this one, this is, I don't have a closure here. Here I have a closure, but I don't have a closure here. So because of B, so this is a fact B. So this is by from here. So this implies A of X. Just the transfer A of X is interior, belongs to the interior of A. In the translation, right? This is the radius Rx centered is 0, but I have a translation by X. So AX is interior of this one. Because this is interior, then there exists the open neighborhood, open ball, radius S of X, positive, such that B, AX, SX belongs to this set. Because this is interior, this one interior of this one, and this belongs to A of G. So here, what I proved here, for every x in here, you can always find S of X such that this one belongs to this. Okay, let me summarize over here. So for every x in G, there exists Sx positive, B, Ax, Sx subset of A of G. Okay, and then I take a union of this union B, Ax. So this guy is actually A of G, because this one is always true. Okay, because you take any element here, so you take any element y in A of G, then there exists the x in G such that Ax equals y, and therefore given this x, we have this analysis. Okay, given x, so there exists Sx positive such that B, Ax, Sx contained in A of G. So which means what? For every y, so this is what B. For every y belongs to one of this one. So this means A of G. Let me remove this part. A of G. So you don't have it here. A of G is a subset of union X in G, B, Ax, Sx. Okay, so this is always a subset of this one. So which implies so that we have A of G is equals to union, arbitrary union of B, Ax, Sx. Okay, this is, but each of them is open set, open ball. So A of G is open. Okay. 자, 지금까지 배운 내용이 오픈 매핑 티어럼인데요. 그 어떻게 증명했냐? 첫 번째 우리가 배운 내용이 이제 이미 R에 대해서 이제 이 인테리어가 A의, 그러니까 A의 BR의 클로저를 취한 집합의 인테리어가 반드시 0을 포함한다는 거고요. 이게 이제 첫 번째 스텝이고, 그 다음에 여기다가 R 대신에 반지름을 2분의 R로 바꿔버리면은 이제 그 참수, 그 값의 차이는 여기 R일 때는 인테리어가 클로즈가 없죠. 그래서 여기다가 반지름을 반으로 줄여대서 클로즈를 취하면 얘는 여기 들어간다는 거고요. 여기 두 번째 스텝이고, 첫 번째 와 두 번째 스텝으로부터 우리가 이제 얻는 결론이 임의의 t에 대해서 interior of a, b, t의 클로즈는 항상 0을 포함하게 되고요. 그러니까 두 번째에서 요거는 요거보다 큰데 얘가 반드시 0을 포함하게 되니까 이제 0이 이 집합의 인테리어가 되는 거죠. 그 성질을 이용을 해서 최종 오픈 세트를 오픈 맵이라는 걸 증명을 이제 하게 됩니다. 제가 한 이 노트는 이제 요 증명은 아마 약간 내가 여러분 다운로드한 그 노트랑 서로 약간 다를 수도 있지만 같은 아이디어입니다. 그래서 요거를 꼭 여러분들이 좀 자세하게 완벽하게 공부를 해 두시기 바랍니다. 네, 수고하셨습니다.